Hello, my name is James Park, and this is my lab 5, the Falling Slinky system. Okay, so the table of contents, so we have the introductions and conditions, equations and key physics concepts, experiment and data, coding and explanation, and analysis and discussion. Alright, the introduction and conditions. The purpose of this lab was to predict the motion of a slinky plus tennis ball system while it's falling and analyze its drop and its effects slash forces causing it. And in the experiment, a slinky that's extended with a tennis ball is attached to the bottom. A slinky that's extended with a tennis ball attached to the bottom is let go at a location 0.54154 meters off the ground. And tracker was used to observe the motion along with glow script to make a predictive model in order to analyze both and determine why the slinky was stationary or not stationary. Alright. The key equations slash key physics concepts were Newton's second law, drag force, velocity update position, velocity and position update position, the spring force, which is the slinky, and the gravity force, which is all right here. Alright, and this is the drag force, which is negative b. It's just like a drag constant times the velocity, magnitude velocity squared times v hat. Alright. The experiment and data. Here's the experiment, where you see the tennis ball and the spring, the slinky, and then the slinky goes down. And as it reaches the ground, it accelerates and goes down like this. The mass was 0.26 kilograms. Derek's height, which is Veritassim's name, was used to calculate the height of the whole thing, which his height was 1.78. And the initial position was this, but we're only focused on the y-axis, which is 0.154, and the initial velocity was 0. Okay. Now the coding explanation. So first part is the initial values. This is the mass is 0.26, which is the mass of the slinky plus the mass of the tennis ball. This is the initial position that's stated, and the drag constant is calculated by just doing trial and effect, and the c vector, which is just a regular value, just a value that I created, just a force value, where that makes it so the force of gravity is greater than the force of string. Because if you look back at the experiment, if you see the graph, you can see that at a certain point, from here to here, even though the slinky hasn't reached the ground, you can see how the movement is still going a tiny bit downwards, meaning that there was a force here meaning that there was more gravity force than spring force. Alright, so then the equation that I used was just the force of gravity equation, right? And then the force of spring, since we don't know the force of the slinky, I made it so it's equal to the force of gravity minus a certain value, which that being c in this case. And then these are the update formula, and this is the same case, but instead of the ft, we use the force of drag, which we just use the drag formula. Right. The analysis of the two graphs. This is the graph that was shown. The blue one being the actual experiment, the observable, and the red one being the one that was solved by the code. And the similarities are that you can see in both of the positions that it just goes down slowly, and at a certain point it just dips down really quickly. And the differences are on the observed one, you can see there's more erratic movement rather than the calculated one. And the possible source of error on this might be, first thing, human error or tracker issues on the observable observable data, incorrect determination of the drag and the spring slash slinky force, the B and the C, because we had to do that by trial and error. Alright, the discussion. So, why does the bottom of the slinky plus ball system not fully affected by gravity until the slinky reaches the bottom? So the force of the gravity in the y direction is less than by the slinky, as the slinky acts like a big spring that counteracts the gravity force with tension slash spring force that's opposite and slightly less than the gravity force. And it has to be slightly less because if you see the observation again, you see that the ball is going slightly below and below, but which means that the forces are down in equilibrium, which means that the gravity force is greater than the spring force. Okay. And unlike doing this experiment with just a slinky, where the slinky would remain stationary, why did the slinky plus ball system not remain stationary, rather go down before the slinky reached the bottom? Okay, so since the system has an extra mass added to it, being the tennis ball, the slinky spring slash tension force was not able to make the force of the gravity of the whole system into an equilibrium. Unlike with just the slinky, where only the gravity force on the mass of the slinky is needed to be equilibrium to the opposite force, which is the spring force. Okay, meaning that subsequently, if the slinky's force was increased by increasing the length of the slinky in the observational or experiment, it could possibly be also stationary. Alright, that was my lab. Thank you.